Hey guys, Dr. Thomas. It's chapter 13, part 2. I'm on slide 12 of the PowerPoint. We're going to explore a little bit of information about why some compounds dissolve in a solution and why others don't. In order to do this properly, we have to be considering thermodynamics. Again, you might review some of your chapter 5 information for this, although I will say we're going to do this qualitatively, not quantitatively. So while we're going to talk about the math, we're not actually going to do any problems with it. Okay? So in order to talk about whether a compound will dissolve or not into a solution, it brings up the idea of spontaneity. If a process happens spontaneously, that means it will occur without outside intervention. For instance, if I add a little bit of sodium chloride to water, we all know that sodium chloride is a soluble compound. So basically, if I add sodium chloride to water, and either I wait or I stir it a little bit, I know the sodium chloride will dissolve. So that would be a spontaneous process. On the other hand, if I add sand to water, I can stir it all I want, and I know the sand's not going to dissolve. Okay, so that's the idea of a spontaneous formation of a solution versus adding an insoluble compound that doesn't dissolve. That would be non-spontaneous. Okay, now to talk about spontaneity, there are two thermodynamic factors that have to be discussed. The first of these is enthalpy, which is delta H. You should remember that from 1211. So in order to form a solution, I kind of have to think about the overall process. What has to happen for a solution to form? Okay, so if we look at this picture, essentially there are three different things that have to happen. First of all, if I have a crystal of a solid solute, say it's sodium chloride, in order to dissolve it, the first thing I'm going to have to do is I have to break apart the particles of the solute. Now, they're held together by intermolecular forces. If I want to break them apart, that's going to require the input of energy. So that step, delta H1, is going to be a positive delta H value, or it's going to be endothermic. Okay? Then, step 2, I have to take the solvent. And let's just say the solvent is water. Again, for the solute particles to get into the solution, I'm going to have to break apart some of the solvent particles from each other. So in order to separate them from each other, again, that's going to require energy. So step 2 will also be endothermic. And then finally, once I've separated the particles, then I can mix the solute particles with the solvent particles. When I put them together, I'm going to form new interactions between the solute and the solvent. Those interactions are going to stabilize the particles. So that's going to be an exothermic process. It's going to release energy. Okay, so essentially I have two endothermic steps. I have one exothermic step. If we remember Hess's law from 1211, we would know that for the overall process, it should be the sum of the three steps that have to occur. So then graphically, we can kind of explore two possibilities here. If the delta H of the first step, separating the solute, and the delta H of the second step, separating the solvent, the net change in energy, if I'm starting at this random value here, I'm going to go up to the maximum. But then the third step's exothermic, it's going to bring me back down. If delta H3 releases more energy than delta H1 and 2 absorbed, that's going to make me finish at a lower level. That's going to be an overall exothermic process. That is a possible way that the energetics of a solution forming can happen. The other option is that delta H1 and delta H2 are larger together than the energy released for delta H3. If that's the case, where delta H1 and 2 are larger in magnitude than delta H3, then I end up with an overall endothermic process. Okay? Now, both of these possibilities can occur. Give an example of each one. If I dissolve sulfuric acid in water, if I take 1 mole of sulfuric acid, dissolve it into a liter of water, then it's going to release 74.3 kilojoules of energy. That energy, as it's released, will go into the overall solution. So basically, if you dissolve sulfuric acid in water, the whole solution is going to get really hot. On the other hand, if I dissolve ammonium nitrate in water, the delta H for that process is positive 26.4. So basically, if I dissolve a mole of ammonium nitrate into water, it's going to suck all the heat in. The overall solution is going to get cold. Okay, this is actually the reaction that's used if you ever buy a cold pack to keep your hands cool or something like that. All right, now to know which compounds will dissolve, we would prefer, for spontaneity, the universe likes energy to be released out into the universe. It doesn't really like for energy to collect in one place. Just natural process. Things like to be dispersed, not gathered together. Okay? So, there are two things we have to look at. For enthalpy, the release of energy to the outside is the preferred direction that the universe likes to go. But we know that sometimes endothermic processes do happen. And the only way we can explain that is we have to think about a second factor. This hasn't come up in chemistry up till now, but it will come up in chapter 19 later. We'll discuss it in a lot more depth. But entropy is the measure of a disorder of a system. The second law of thermodynamics says that the universe is always moving toward disorder. Okay? So we kind of have two different things to look at here. The energy wants the energy to be spread out, and it wants for systems to be disorganized. Well, there are cases where both those can happen, and those things are definitely going to be spontaneous. If you release energy and make things disorganized, that will always be a spontaneous process. Okay? But if it's endothermic and increases the disorder, that may or may not happen. If it releases energy but increases the order, that can happen too. There's a lot of math involved in that where you have to play with the numbers and see which one's bigger. That's actually what we're going to do when we get to chapter 19. When we get to chapter 19, we have an equation we're going to use that's going to put these two values together, and then we're going to calculate what's called the free energy. Okay? The free energy is called the Gibbs free energy. It's actually going to be our predictor for which things are going to happen spontaneously or not. Okay? Now, for now, we need to apply this to a solution. Okay, so how does this factor into a solution? Well, we already said formation of a solution can be endothermic or exothermic. What about entropy, though? When we form a solution, does it increase the entropy or does it decrease the entropy? Well, at first sight, we would usually say, if I want to move toward disorder, if I look at the picture up here, I have my solute and my solvent. If they are separate from each other, that's a level of organization. So the solute and solvent separated, it seems like it's a very ordered situation. When I mix them together, things are all mixed in, that's much more disorganized. So at first glance, it seems like formation of a solution would always be an increase in the disorder. Okay? That's usually true. But I will say there is another factor. When we form a solution, the molecules are all not randomly arranged. If we talked about solvation and hydration, if you remember, whenever sodium chloride dissolves in water, the sodium ion actually gets surrounded by water molecules, and all the water molecules are turned so the oxygen is the negative on the oxygen is closer to the positive on the sodium for all these water molecules. And then the same thing on chloride. All the water molecules are turned the same way, where the hydrogen is closer to the chlorine. Okay? That is a level of organization that didn't previously exist in the solution. So while we did in sodium chloride, we broke up the crystals, which is increasing disorder, but then we formed these hydration spheres around the ions, which is increasing the order. And the question is, which one's more significant? Okay? Again, mathematically, we're not going to get into all that really right now, but just the idea, the heat change is important in the formation of a solution, but also considering how organized the molecules are we increasing the disorder or decreasing the disorder? Both of those things have to be factored in to determine whether something is soluble or not. So we're going to move on from that. Again, have an idea of qualitatively how that works, but don't obsess about it too much. Moving on, so now we're talking when we form a solution. If something dissolves in water or any solvent, we say it's soluble, but we also want to talk about, okay, how soluble is it? we want to be able to assign a numerical value for the solubility of a solute that can exist in a solution. Okay? For instance, I know that sodium chloride is soluble in water. But the question is, how soluble is it? So if you give me the solubility, it means that you can dissolve a certain amount of salt into a certain amount of water, and that's going to be the maximum amount you can dissolve. That's what we refer to as the solubility of a compound. Now, some important terms that are going to relate to this next section. If you mix two liquids together, if they will mix together in any ratio, those two liquids are called miscible. If two liquids won't mix with each other, that's called immiscible. Okay? Now, miscible, like if I mix ethanol and water, ethanol is drinking alcohol, I can mix together a 50-50 mixture of the two. I could have 90% ethanol and 10% water. They will mix. I could have 90% water and 10% ethanol. They'll mix. Okay? I can mix any ratio I want between ethanol and water, and they will always fully mix with each other. Excuse me. So I could say ethanol and water are miscible. They mix in any ratio. On the other hand, if I mix together hexane and water, hexane is nonpolar, water is polar, they don't like to mix much at all. So if I mix them together, they form two separate layers in the container. Those liquids are immiscible. Okay, now, a trick here is, even though we say they don't mix, actually, there's always a little bit of solubility for every two compounds. When I mix these two together, a tiny, tiny little bit of the hexane will probably mix in with the water, and a tiny bit of the water will actually go into the hexane, okay? But it's a really, really low number, so for the most part, we just say they are not soluble with each other. These two liquids are immiscible. Okay? Now, other words, saturated, if I add enough solute to reach the maximum amount that could dissolve into a solvent, that would be a saturated solution. Okay? Anything less than the maximum is going to be called unsaturated. And then finally, there are special cases where we could form a supersaturated solution, although those are very unusual, so you have to be careful with that one. Just because I mix, if I dump in a bucket of salt into a small amount of water, only a certain amount can dissolve, and anything I add above the solubility limit is actually just going to settle to the bottom. Okay? I don't form supersaturated solutions except under very specific conditions, and usually that has to be described to you before you would assume that you're forming one of those. All right, so this graph, basically it shows that the solubility of several compounds does change with temperature. So if we take a close look at the graph, on the y-axis is listing the solubility of a group of compounds. The units are the grams of a salt. They're all salts. So the grams of salt per 100 grams of water. On the x-axis, we have temperature. So essentially what we can see here is that each compound, as we change the temperature, the solubility increases for most of them. Although I do have one, cerium sulfate, that the solubility goes down. Okay? But a general rule we can learn here, the solubility of most solid compounds will increase with temperature. That's something that you should know. Now, why is that? Well, when we get into chapter 15, we'll talk about equilibrium. Essentially, anytime something that's endothermic, when you add heat to it, it's going to actually push it to the product side of a reaction. So when we add a salt, if it's an endothermic process, it's then increasing the temperature is going to raise the solubility. Okay? On the other hand, if it's exothermic, then adding heat actually discourages the solubility. So cerium sulfate, as you add heat, the solubility goes down because that one's an exothermic process. So let's read the graph a little bit. If I wanted to use this graph to determine the solubility of KCl at room temperature, I'd say, first of all, what's room temperature? That's 25 degrees Celsius. I'd have to find KCl on the graph, which is this blue line right here. At 25 degrees Celsius, go up to the blue line. I would say the solubility of KCl, pretty close to 35 grams per 100 grams of water, maybe 33. You have to estimate that the best you can. So let's just say 33 grams of KCl could dissolve into 100 grams of water. That's the solubility of that compound. So then you ask the question, well, how much KCl could be dissolved into a specific amount of water that's not 100 grams? Okay, so how can I do that calculation? Well, essentially, I would set up as proportions. I would read the graph and say, I know it's 33 grams of KCl per 100 grams of water. So then I could solve for the amount of KCl that could go in 58 grams by setting up proportions. I would do 33 over 100 equals x over 58. And then if you solve for x, that would be the amount of KCl that could be dissolved into that much water. So if we solve that, let's see, let's go ahead and do it on the board real quick so we have the answer. So my math would be 33 grams KCl per 100 grams of water equals x grams over 58. So the answer is I got 19.1 grams of KCl could dissolve into that solution. So, follow-up question. Well, we just said that 19.1 grams could dissolve into 58 grams of water. So what would happen if I dumped 50 grams of KCl into 58 grams of water? Okay? Now, if you think, oh, well, if only 19 can dissolve, so if I add 50, that means it's going to be supersaturated, then you forgot what I said a couple minutes ago, where we don't normally form supersaturated solutions. Okay, that's a weird situation that we'll get to soon. On this one, though, I would say when I dump the KCl in, 19.1 grams will dissolve into the solution. The rest of it will all just settle to the bottom. And I could subtract 50 minus 19.1, and then I could actually figure out how much solid is actually left over on the bottom. And I think it'd be 30.9. All right, so what about supersaturated solutions? Okay, so this picture shows a supersaturated solution of sodium acetate. Now, it looks just like every other salt solution. It looks like water. But the trick here is the amount of sodium acetate that should be able to dissolve in that solution, somehow we have tricked the solution into allowing more to dissolve. How do we do that? Well, usually what you do, just like if I was making iced tea, if I want to make sweet tea, I heat the tea up to boiling, I add the sugar, and the reason we add the sugar while it's hot is that things dissolve better when it's hot, and then I let it cool down to room temperature, or I add ice before I drink it, right? Well, if I do that process very carefully, where I heat a solution up to a high temperature, and then I add my solute, since the solubility of the compound is much higher at high temperature, I can add a lot of solute to the solution, and then if I very carefully cool it down slowly, and don't shake the solution, don't stir it, don't create any turbulence in there, then what can happen is I can cool it down. As I come down, the solubility limit decreases, and I might cool it down to the point where all of a sudden I have more in the solution that I should be able to have, but the solution will sometimes, it'll have trouble forming the first crystal of the precipitate that's supposed to come out. And if it can't form that first crystal, then it can get to a lower temperature where it should have precipitated out, but it can't, and that's what a supersaturated solution is. Okay, so then a cool thing happens with that. If you do something to disturb the beaker of a supersaturated solution, sometimes you can take a glass rod and like scrape it to create a little friction, or you can add what's called a C crystal. So they add basically one tiny little crystal, you add it to the solution. All of a sudden, that helps the solution overcome that barrier where it couldn't form the first crystal because you're giving the crystal to it. And all of a sudden, all the extra sodium acetate all tries to come out at once. And you form these big, long crystals that are really cool. It's actually a very pretty demonstration to do. But all the extra stuff comes out, and it brings it down to be a normal saturated solution, and all the precipitate eventually would settle to the bottom with all these crystals. So, last thing, talk about miscibility and immiscibility. So, when we look at alcohols, so in organic chemistry, alcohols are a class of compounds where you have carbon atoms, sometimes a long chain of carbons, and then you have an OH group, which we know that an OH group can have hydrogen bonding. So if I have the smallest alcohol, which is called methanol, that means you have one carbon, 3 hydrogens, and then the OH. That is an extremely polar molecule. It has hydrogen bonding. It mixes with water infinitely, which that's kind of like ethanol earlier. No matter what ratio of methanol and water you mix together, they will always mix with each other. Okay? The second alcohol is ethanol. It also mixes with water in any ratio. But if I get to the third one, actually the third one still, if I get to the fourth one, what I notice with the fourth one is all of a sudden the solubility is no longer infinite. When I get to butanol, the solubility now has a fairly low limit. And the reason for that is, even though all the alcohols have the OH group, which is the hydrogen bonding, as I make the carbon chain longer, if you remember hydrocarbons are nonpolar, the OH is extremely polar. What happens is, as the carbon chain gets longer, the properties of the carbon chain start to dominate over the properties of the OH. In a small molecule, the OH is more important. But the bigger the molecule gets, the more important the carbon chain becomes. Okay? So as we go down the table, getting to larger alcohols, what we see is that the solubility of the alcohol in water decreases, but then the last column, the solubility in hexane, which is a nonpolar solvent, the longer alcohols are going to have a very high solubility in a nonpolar solvent. Okay? And then that brings us to, okay, when we look at these compounds, so vitamin A, again, if you're going into biology, pharmaceuticals, medical applications, stuff like that, some vitamins are called water soluble and some vitamins are called fat soluble. So vitamin A is a fat soluble vitamin. How do we know that? Well, of course we can observe it, but if we look at the structure of vitamin A, what we see is that most of the structure is just a hydrocarbon. I mean, the different, the hexagonal ring and the double bonds and everything don't really matter. I have carbons and hydrogens everywhere on that side of the molecule. I do have an OH, but it's such a small part of the overall molecule that this molecule tends to be fairly nonpolar in nature. It is dominated by London forces instead of the hydrogen bonding in this little bit right here. So it's going to be more soluble in a polar solvent, which is why we say that that vitamin is fat soluble. That's important because if a person consumes too much vitamin A, if something is water soluble, your body is really good at flushing it out, and like it flushes through your system and comes out in your urine if you have too much of it. So vitamin C is water soluble. You can eat as much as you want. It all gets flushed out. Vitamin A is fat soluble. When you eat too much of it, it gets absorbed into the fat in your body, and your body doesn't purge the fat very much at all. So therefore, it can build up in your body and cause problems. Okay? So this is vitamin A. Over here we have vitamin C. Now again, I just said vitamin C is water soluble. Again, I've got lots of carbons and hydrogens, but I've got an OH here, an OH here, an OH here, an OH here. Now there's enough OHs in there that the properties of the OH groups are going to dominate the behavior of this compound. This compound is very soluble in water as opposed to vitamin And that's a good place to quit. We're about to get into some more math in the next section.